Okay, good afternoon, everybody. We are Ferrous Solutions, and our Capstone project was working with Ferrofluids for oil spill cleanup. I'm Sarah, this is Courtney, Anila, and Mary, and as a team we make up Ferrous Solutions. So right now, with the increasing consumption of oil worldwide, there's an increase in production of that oil. And in the U.S., every year there's about 1.3 million gallons of oil spilled into the U.S. waters just from day-to-day production. And this doesn't include the big oil spills like the Solomon oil spill that's occurring right now and the famous BP oil spill in 2010. So right now in the Solomon Islands, over 2,000 gallons of oil have been spilled into the Pacific Ocean. And it's estimated right now that $50 million is going to be required to clean this oil up. Right now there's also, they don't know the implications on the environment yet because it's still going on, so that still is yet to be determined. Most recognizably, the BP oil spill in 2010, over 200 million gallons of oil were spilled into the waters of the Gulf of Mexico and costed BP oil, the U.S. government, and the U.S. taxpayers over $62 billion to clean up. Even today, we're still seeing environmental implications almost 10 years later. Current methods of oil spill cleanup, all of which were used in the BP oil spill, are burning off the oil, which is successful in containing the oil in the ocean, but it also releases all of those toxic chemicals that are in crude oil into the air and the environment surrounding the oil. Additionally, chemical dispersants are often used, which add additional toxic chemicals to the waters. Most notably, co-Rexit is one of the most common chemical dispersants that is used in oil spill cleanup, but it's very toxic and carcinogenic and is actually known to have caused cancer in some of the workers who were cleaning up the BP oil spill. Also, oil booms are kind of a contraption used to stop the oil from spreading in the ocean, but they also act as a barrier to the marine wildlife that lives in the ocean in that environment. And so what Ferrous Solutions is proposing to do is use Ferrofluid technology to clean up oil spills. What a Ferrofluid is, it's a fluid containing iron oxide nanoparticles, and those nanoparticles give the solution its magnetic properties. Additionally, Ferrofluid is also non-toxic and is compatible with many different types of surfactants and carrier liquids, which makes it desirable to be used in oil spill cleanup because we're not adding to the toxicity of the event. So what Ferrous Solutions will do is we will be able to dispense our produced ferrofluid into that spilled oil, and then that will essentially magnetize the crude oil that was spilled into the ocean, where we can then pull it up with a magnet. So the goal and scope of this project is to scale a process that can produce 200,000 kilograms of nanoparticles on a yearly basis to be dispensed in a compatible carrier liquid to be able to clean up that 1.3 million gallons of oil that's spilled into the ocean on day-to-day production. This 200,000 kilograms of nanoparticles will be able to give us a 1:19 ratio of ferrofluid to spilled oil, which from different literature sources we determine is the optimal ratio for us to effectively remove that oil. So as a company, our vision is to impact the world by cleaning up potential oil spills with non-toxic ferrofluid to protect marine life and the environment.
Ferrous Solutions will operate as an LLC in order to develop, manufacture, and market our ferrofluid. We hope to become the leader in bulk manufacturing of ferrofluid. We plan on selling our product to oil companies, offshore drilling companies, as well as the U.S. government and oil cleanup companies because these are the people who paid for the BP oil spill cleanup, and we'll market our product as affordable and also environmentally friendly. So looking at our competitors, Ferrotech is currently the leader in manufacturing ferrofluids, but they sell their product on a smaller scale, at a scale of a milliliter, and they're selling at $4 to $10 per mil. But looking at the oil spill cleanup market, we have Elastic that develops skimmers that range at a price of $100,000 to $300,000, and we also have Chemtex that created the oil booms that cleaned up the BP oil spill that cost around $400 per spill kit. And then we also have Nalco Environmental Solutions that developed Corexit, which is a chemical dispersant, which was used in the BP oil spill that is around $44 per gallon. But as Ferrous Solutions, we plan to sell it at 42 cents per mil. We put it as a milliliter here just for an even comparison in the table, but we actually plan to sell it at a larger scale of a liter, which will be priced at $420. So we originally got our idea for a ferrofluid to clean up oil spills from this Avco Corporation patent, which was acquired by Ferrotech. They create a non-magnetic iron slurry that is then magnetized by a detritor. Their particles are iron oxide and magnetite, and they're sized around 30 nanometers. There's also MIT that currently has a patent regarding separation techniques of removing the oil from the ocean. They use permanent magnets as well as magnetic filters and meshes with their magnetic fluids, but they currently don't have any claims regarding their formulation of these particles.
So now we're going to talk about the lab scale experiments that we ran in Professor Webster's lab. So the way that we're different than the patents that Anila just talked about is that we use the co-precipitation method, which includes combining iron chloride salts with sodium hydroxide, a base, and then you precipitate out a sodium chloride salt and your product, which is iron oxide. So we ran 4 different experiments to determine the optimal procedure for making these nanoparticles, and our optimal procedure is shown here. It includes mixing iron chlorides in hydrochloric acid solution. We did this because we didn't want our reaction to occur too early or with anything that it shouldn't react with. So putting it in an acid, make sure that that doesn't happen since the reaction occurs with base. We also, we combine this acid mixture with sodium hydroxide in an inert environment. We use nitrogen gas bubbled into the water to degas it, again to make sure that our reactants didn't react with oxygen. And then we increased the temperature to 70 degrees Celsius and vigorously stirred for 5 hours. And then after that, we added a surfactant, which we used oleolamine, but that could be optimized in the future. So these are some experimental parameters that we varied throughout our different experiments. The first one was the presence of the acidic conditions with our reactants. We didn't do that in the first experiment, and we also are sure that we didn't add enough base, so we didn't create magnetic particles. The second trial, we had acidic conditions for our reactants, and we calculated out the amount of base instead of just using pH paper as we did in the first experiment. So we made sure that our reaction went to completion. We could tell that because there was a pretty noticeable color change. The whole reaction turns black instead of like orange. And we also reacted the particles for 5 hours and did not add surfactant. And then the third trial, we had acidic conditions at first, ran the reaction for 2.5 hours and did not have surfactant. So this reaction time is really important because if we could decrease from 5 hours to 2.5 hours, we could really increase our efficiency and decrease the amount of money that we're spending to make our product. Then for trial 4, we had acidic conditions. Our reaction time was 5 hours, and we added surfactant. So now I'm going to talk about the data analysis that we ran. So we ran VSM, which is vibrating sample magnetometry, on the trials 2, 3, and 4 because trial 1 wasn't magnetic, so we didn't run it. You can see on this graph that the highest specific magnetism that we got was trial 4, which had the 5-hour reaction with oleolamine surfactant. We also analyzed these particles on TEM, which shows the size and shape of the particles as well as how much agglomeration is occurring. So we saw that throughout all the trials we had around 10 nanometer size particles and they're all spherical, but you can see between the image on the left and the right that there's significantly less agglomeration in trial 4, which is the right image. This is really important because these particles are magnetic, so they easily attract to each other, and having a higher surface area available makes a higher availability of that magnetic core of each particle, so it increases the overall magnetism.
So the scope of our project included an initial formulation and taking the best procedure for that and scaling it up for our plant design. But of course we want to make sure that this is a viable solution for what we propose that it's going to be used for. So we did a couple proof of concepts. So when we were taking our oleolamine coated particles and putting them into solution, vegetable oil as the carrier liquid, As our ferrofluid, we saw that they dispersed pretty well, but we wanted to make sure that the oleolamine surfactant was really doing what it was supposed to be doing, which is creating a layer of hydrophobicity around the particles so that they wouldn't come out of solution of the oil-based solutions, so that it wouldn't, theoretically go into the ocean where the water's polar. So what we did for this was a little miscibility vial test where we took 5 milliliters of water in one vial and 5 milliliters of vegetable oil in one. We pipetted 125 microliters of our ferrofluid solution into each of those, shook them, and then let them settle. And the picture you see here is after 1 minute of settling. The picture on your left is with the water, and the picture on your right is with the vegetable oil. So you can see that the ferrofluid is immiscible in the water and miscible in the vegetable oil, of course. So that proved that this is probably a pretty good solution for going into the ocean. So that being said, we wanted to do another proof of concept, which was a kind of a Petri-sized dish simulation. So we used water and food coloring to simulate the ocean. We took 5 milliliters of vegetable oil and gasoline to simulate crude oil. We pipetted 1 milliliter of our ferrofluid onto that, shook it around a little bit, and then took a magnet and tried to just take one pass and see what we would come up with. So we got most of the particles and a little bit of the oil spill, but of course not all of it, so that would be something that we could optimize with the formulation and of course the mechanical means also of taking it up. So this is just a summary table of our trials 2 through 4, which produced the iron oxide nanoparticles. You can see that regardless of reaction time or the presence of surfactant, that the average particle size and the specific magnetism don't really vary that widely, but the key standout here is trial 4 and the presence of surfactant, which gives us a lower level of agglomeration. So we decided for our scaled up design that we were going to go with the trial 4 conditions, which include the presence of the oleolamine surfactant, and conservatively we were going to use a reaction time of 5 hours. So I have a little sample right here of our ferrofluid and a magnet, so if you want to play with it and see that it is in fact magnetic.
So next I'll go into our plant design of our scaled up process. So we have 3 jacketed batch reactors that are lined up in parallel. We have our iron salts mixed with hydrochloric acid, our sodium hydroxide and water mix, as well as additional water, all being pumped into our 3 reactors. We also have nitrogen gas supplied to our reactors to maintain that inert environment. From all the products from these reactors are pumped into a continuous centrifuge. The supernatant from the centrifuge will be pumped through an RO system where any waste or unreactive materials will be removed, and we will recycle that clean water. From the bottom of the centrifuge will be our particles, which will be pumped into a mixer where it will be mixed with oleolamine, our surfactant, as well as the carrier liquid. After this, our ferrofluid product will be pumped to a holding tank where it will be stored until it is packaged and distributed. So our reactors are sized at 4,000 liters each. Our centrifuge has a diameter of 0.5 meter. Our holding tank has a capacity of 500,000 liters. Our pumps have a flow rate of 30 liters per second, and our mixers range from 500 to 10,000 liters, and our RO system can filter up to 20,000 gallons per day. All of our equipment is a non-magnetic stainless steel because our final product is magnetic and we do not want our system clogging.
So our plant is going to be located in Dallas County, Texas, on a 70-acre plot of land. This is because a lot of oil refineries are in Texas and the BP oil spill occurred in the Gulf of Mexico. We're going to run at 3 batches per day, 5 days per week, 50 weeks per year. This is at 3 shifts per day and 4 operators per shift under proper supervision. This gives us 200,000 kilograms of iron oxide nanoparticles per year. So here's our PNID. Just some things to note are the control systems on our 3 reactors. So we have temperature, pressure, and level controls on each reactor so that we will be notified if anything goes out of range, and just have safe operations in place. We also have dump valves at the bottom of each reactor. This is if the process shut down, we could still get our product out of the bottom of the reactor instead of just losing all of it. And then we also have pressure relief valves at the top of each reactor. So if our pressure increases too much, it'll be relieved and a reactor explosion shouldn't occur. And then some other control systems that we have are level controls on the mixer and the holding tank, and then concentration controls on the reverse osmosis system. And then another thing to note is that all of our valves are fail closed because we don't want the liquid to just be pumped through the system and overflows to happen or like unwanted reactions to occur. So here's an SDS summary of all of the reactants that we use in our process. Although our product is basically non-toxic, some of the reactants that we use are toxic. So ferrous chloride and ferric chloride both have health hazard ratings of 3s and 2s, and then sodium hydroxide and hydrochloric acid are both corrosive. So to mitigate these hazards, we will make sure that our operators are properly trained, they're wearing adequate PPE, and everything that can be charged and pumped into the reactors and the mixers will be automated like that. And then olealamine, our surfactant, is flammable, but the flash point is 154 degrees Celsius, and that is much higher than what we run our process at. The highest temperature that we reach is 70 degrees Celsius. And then one more hazard that could occur is that our iron oxide nanoparticles are powder, so an inhalation risk could happen. So we just make sure that our operators are wearing masks and are properly trained. So we did an FMEA to figure out like where in our process failures could occur and where they're most likely. We saw that our material handling, as I talked about a minute ago, is probably the most important safety aspect. And as I said, we'll just make sure that our operators are properly trained, they're wearing PPE, and anything that can be automated will be automated, so they're not working directly with a lot of chemicals. Our reactor temperature and pressure could also go out of range and cause an explosion, but we have temperature controls, pressure controls, and dump-in pressure relief valves to mitigate those hazards.
So now we're going to talk a little bit about the economic feasibility of this project, because obviously when you're trying to push a new solution to something that's already a big problem, cost is a driving factor. So this table here summarizes our reactant material cost. So this is just the cost to produce the iron oxide nanoparticles themselves. We have everything from the reactant materials all the way down to the nitrogen gas that keeps the reactors inert. And this is a batch size of 10,000 kilograms of reactant materials. So that produces about 279 kilograms of nanoparticles per batch. The per batch cost is a little under $100,000, but the annual cost we are calculating to be about $73 million per year. This table summarizes the cost of making the ferrofluid itself. So again, that 73 million number is right here, showing that the bulk of the 79 million annual cost that we are projecting is really coming from those nanoparticles. We based it off of our lab scale formulation, which had vegetable oil as the carrier liquid and olealamine as the surfactant. But obviously with optimization, we would probably not be going with vegetable oil as our carrier liquid, but it's definitely an option. We don't expect this cost to increase or decrease by that much, just because the bulk of the cost is really coming from the nanoparticles themselves. And this is a summary of our equipment costs. We have everything from the batch reactor all the way down through the dump relief valves and the piping itself. About 35% of that 2.2 million total cost comes from piping, and another 40% is coming from the batch reactors and the centrifuge, which are really the two main unit operations. We have 3 batch reactors and they're all jacketed, which is why that cost is so high. And the centrifuge we really tried to cost as high as we possibly could, because there's really nothing right now available for industrial scale of nanoparticles. So we'd probably have to come up with a custom solution with a vendor. So we're expecting that cost to be pretty high.
So looking at economic projections over 20 years of production, we estimate that our net present value after 20 years of production is going to be $71.2 million with an internal rate of return of 92%. And this is based off of selling our ferrofluid product at $420 per liter, which will give us a gross revenue of $111 million per year. So subtracting out all of the depreciation, taxes, and operating costs, and packaging and distribution, we'll be having a net profit annually of $17.4 million, This is also assuming that our first year of production will only be operating at 50% capacity to anticipate any optimization needs that we'll need to have. So looking at our process overall and looking at the preliminary experimentation that we've been able to do, we were successfully able to produce iron oxide nanoparticles that had an average specific magnetism of 12 EMU per gram, as well as a particle size of 10 nanometer. And then from our proof of concept studies, we were able to determine that our ferrofluid was immiscible in water but soluble in an oil-based solvent. And this gives us confidence that we'll be able to dissolve it well in the crude oil that's spilled into the ocean to then be pulled up with a magnet. In terms of economics, our initial capital investment that's required is $12.6 million, and we will have an annual net profit of $17.4 million by selling our product at $420 per liter. Looking in the future towards next steps after our proof of concept experiments, we look to vary the amount of surfactant as well as the type of surfactant and carrier liquid to make our ferrofluid have a better affinity to the spilled oil in the ocean. Specifically looking at the structure of the surfactant, carrier liquid, and crude oil, if we match it more towards the hydrocarbon chain as well as the functional groups, our ferrofluid is going to have a better affinity and make the removal process much more efficient. In terms of the reaction time, Mary and Courtney mentioned that it's a 5-hour incubation time, but if we were able to reduce that to 2.5 hours or even lower, we would be able to save time and money and potentially increase our production capacity. So future experiments will also look into taking time points throughout the reaction and analyzing those nanoparticles based on our optimal parameters. So before we conclude, we wanted to have a couple of shout outs to some very important people who have made this possible over the last 4 months, specifically our mentor Larry Seidler for giving us timely feedback even on vacation sometimes, Professors Pfluger and Webster for the class overall, and PhD candidates Nicole and Baron. We wouldn't have been able to do it without you for helping us optimize our experiments in Professor Webster's lab. So that concludes our presentation. We'd be happy to field any questions or comments.
Found in the research any sort of like functionalizing of the nanoparticles? Because it seems kind of like it's relying on like their surface area and their affinity for staying in solution to like bond to the oil. So like, I was wondering if you found anything where it's like hydrocarbon chains being attached to nanoparticles, stuff like that.
Didn't like dive into that really so much. We really kind of were focusing on the use of surfactant and hoping that that could do it. In the lab scale, what we actually did was we made the particles in the little reactor itself, and then we added the surfactant in there, and then we lyophilized them and dried them down. But in the process that we have, we would be creating the nanoparticles and then sending them to the centrifuge and then mixing them later with a surfactant and a carrier liquid. So we differ a little bit there, just because I think that the scaled up procedure of using a surfactant later on and adding that would be probably a little bit easier, but that's definitely an idea we'd be willing to look into in the future.
So this is hopefully something with a demand that fluctuates a lot. So you have a big oil spill and the demand skyrockets. How are you going to deal with that kind of fluctuating market demand for your product?
I think
So for our initial scaled up process, we wanted to target kind of the day-to-day production spills. But in the future, hopefully, by potentially reducing the reaction time, we'll be able to increase the capacity of our plant and hopefully anticipate, not hope for, but like anticipate any bigger spills in the future.
And as we showed earlier, there's multiple ways. There's not just one way of cleaning up the oil spill too, so we at least hope to like aid in that.
I'm just curious about this. Did you find anything in your research that said you could, well, pretty much do the same thing, but with iron carbide or like iron carbonate nanoparticles? Just because those are also like really magnetic and more readily available. I'm just curious.
So we did not actually. We just kind of focused our field on like iron oxide and magnetite particles, but those are probable. They probably would work if they are magnetic, and then just put it in a liquid and as surfactant.
you say you're running at like 50% capacity the first year. Are you just going to ramp up to 100 like in the second year, or do you want to go up gradually throughout the first year, or go up gradually after the first year?
Our economic projections say that we just step up to that 100% capacity, but I think that's also included in the optimization during the first year, just having the room for that.
Right.
Yep.
Yeah, early on, in developing a case for action, you were describing the use of Corexit and other dispersants. And I know there's a lot of information about the health and safety of such products. Having sold the raw materials to Nalco at the time, I can tell you that the raw materials are not considered to be carcinogens. So it does raise an issue that I wanted to share with the whole group, because this is very common amongst young researchers looking at issues and evaluating the issue as it's perceived by the public versus as it's being viewed by an engineer or a scientist. And so, like even this morning, the group that I had entered, they had a bioplastic, and several months back, the case for action was, I'll exaggerate a little bit, plastics are bad. And while the plastics have issues, there's a whole kind of cost-benefit analysis that has to be considered when you look at shortcomings of certain products and in particular their impact on human health and the environment, because that very same product can also bring benefits. So if you just attack that one vulnerable spot, you can in some ways misrepresent the magnitude of the issue. Similar kind of thing with fracking. Oh, it creates all this polluted water, and we're getting methane gas going into the aquifers around the country. Well, maybe there were some of those cases, but as engineers and scientists, we have an obligation to really get the data on those things before we buy in to what the kind of the general public consensus might be. Because what you're going to find in your jobs is, when it comes to most of your businesses, there's going to be a negative perception of it. And much of that is unfair, if not all of it. It's due to lack of understanding and the way the media tends to treat these things. So I'm not trying to knock you guys. It seems like it's a common thread across a lot of these solution-oriented presentations. It's not to say that there aren't problems. There clearly are problems, but how you state that problem with the appropriate amount of cost-benefit balance is something that I would challenge you to try to do as you do this kind of stuff in the future. Does that make sense?
Yeah.
Yeah, I hope I'm not talking about lecture. I had a lot of these kind of conversations in business. I'm talking to the public, talking to regulators, talking to academia about what's really happening when it comes to issues such as these and many others.
Thank you. Anybody else? I just had one on your PNID.
Do you want us to go back?
Forgot that it was Spanish.
I see an into your final tank, but no out.
So we costed packaging and distribution, and we sized it, but we ultimately didn't come up with how we were going to do that and when we were going to do that, just because of our production ramp-up rates and marketing and things like that. But that's something that we think about in the future.
I'm just thinking, just sitting there looking at the ins and outs, and I was like, oh gee, I don't see the out, so I guess it's all just going in and staying there. So maybe even just a
box.
yeah, it's in a box, right? Even just with a valve.
Yeah.
2 question mark, doesn't matter, but just to have an out just could be helpful.
Good.
With a valve. An easy 30-second fix, I hope. That's it.
Library.
Anybody else have a question? Oh, one more.
You said like the centrifuge you wanted to use might not exist or something like that. Should use a magnet.
I think that like ultimately we would have something that was magnetic at the bottom. There's so many different centrifuges you can use, but it kind of narrows as your scale grows, and especially also as your particle size shrinks. So there'd probably be something that we'd have to figure out, but I'm sure there's work being done on it somewhere.
The centrifuge that we actually used in the lab was magnetic, and so when we did centrifuge it, it would come down really quickly because of the magnetism. So it was actually pretty easy to take off the supernatant because of that.
Anybody else? No? Thank you.